Welcome to our first webinar. This webinar is about multi-parametric surface plasmon resonance, MP-SPR, which is one of the techniques that we have in our facility, the BioLab. The BioLab is located at the Navi School of Sciences and Technology and gathers in a single unit a unique set of state-of-the-art biophysical and biological techniques, namely circular dichroism, differential scanning colorimetry, flow cytometry, microscale thermophoresis, and MP-SPR. If you are interested in knowing more about us, our website is in the description box of this video. In this presentation, I'll show you what MP-SPR can measure, what are some of the applications of this technique, the theory behind it, the difference between MP-SPR and traditional SPR, some practical advice to design your experiment, and some application examples for life sciences as well as material science. Let's start by talking about what can MP-SPR measure. With MP-SPR, you can gather information about layer properties and molecular interactions. In this table, written in black, are the properties that you can measure with traditional SPR and MP-SPR, and in blue are the properties that you can only measure with MP-SPR. In layer properties, we have the refractive index, thickness, extinction coefficient, density, surface coverage, swelling, and optical dispersion. In molecular interactions, we have affinity, kinetics, concentration, adsorption and absorption, desorption, adhesion, and with the specific add-on, electrochemistry. MP-SPR has a wide range of applications both in life sciences and in material science. In life sciences, this technique is used in pharmaceutical studies, in biosensor development, and in biomaterials and coatings. In material science, is used, for example, in the study of thin solid films, soft materials, and sensing. To better understand the SPR theory, we have to talk about some specific concepts, such as the plasmon. Metals contain a lot of mobile electrons at their surface, forming a free electron gas that can be excited by light, which results in a surface plasmon. A plasmon is therefore an electromagnetic wave propagating along the surface of a thin metal layer. Almost every commercially available instrument, including our MP-SPR Navi, uses a detection scheme called the Plasmon configuration. In this setup, a light source passes through a prism, reflects off the backside of the sensor chip surface and into a detector. At a certain incidence angle, known as the resonance angle, light is absorbed by the electrons in the metal film of the sensor chip, causing them to resonate. These resonating electrons, also known as surface plasmons, are sensible to the surrounding environment. The result is an intensity lost in the reflected beam that can be seen as a dip in the SPR reflection intensity curve. The shape and location of the SPR dip can be used to convey information about the sensor surface. In this example, a binding event causes a shift in the location of the dip in the reflectivity curve. Another powerful aspect of the SPR technology is its ability to observe the time-dependent binding interactions between molecules. By monitoring these changes in the SPR response over time, we can study the kinetics of molecular binding events. Now, how does multi-parametric SPR differ from traditional SPR? We already talked about what SPR can measure. MP-SPR provides all of the traditional SPR parameters and also optical and physical properties of layers. MP-SPR provides measurements in a wide angular range, enabling all SPR curve monitoring, while traditional SPR measures only a small angular area. MP-SPR follows peak minimum position, total internal reflection, as well as peak minimum intensity parameters to get more information about the interaction, while traditional SPR only measures peak minimum position. MP-SPR allows measurements in gas and in liquid, even with organic solvents, while traditional SPR is applied only in liquids. The additional wavelength in MP-SPR results layer thickness and refractive index, and allows for measurements from ultra-thin to thick layers, which is not possible with traditional SPR. This is our instrument, the MP-SPR Navi 208, meaning bear in Finnish, from Bionavis. It allows for 4 simultaneous measurements in 2 fluidic channels, has 2 wavelengths enabling detection of thickness, refractive index, and conformational changes. This instrument has a wide angular range. One scan encompasses the liquid and gas environment and is equipped with an additional gas flow cell. Has controlled liquid flow conditions with a peristaltic pump, and manual filling of injection loops is required, and you can do parallel injections into both flow channels. Let's talk more particularly of MP-SPR in life sciences. As previously mentioned, SPR is a powerful technique to measure biomolecular interactions. It is real-time and label-free. However, you have to immobilize in the sensor surface one of the interactants while the other is free and passes over the surface. This graph, the sensorgram, follows our response over time and will allow you to calculate affinity and kinetic parameters. As mentioned, the ligand must be immobilized on the sensor surface. This can be done by several methods, such as direct coupling, affinity capture, membrane anchoring, etc. Your ligand can be big or small, such as a peptide, a protein, nucleotide, drug molecule, an antibody, a liposome, or even a cell, and the analyte may also vary. It can be a protein, a peptide, a drug, a cell, or even a gas molecule. Now, I will tell you more about how to design an experiment. The first step is, of course, make sure that the equipment is clean and is appropriate for what you want to do and your goals. Then, you have to choose what kind of sensor slide you want for your experiment, and depending on that, the mobilization strategy. Then, define your experiment conditions, result analysis, and finally, a report. The sensor slide, or sensor chip, is constituted by a glass layer, an adhesional layer that binds the plasmonic layer to the glass layer. The plasmonic layer is the metal layer. Usually, the metal is gold, but you can also have silver or platinum or other metal. On top of the metal layer, you can have other materials, such as an inorganic layer or some kind of biochemical functionalization, such as carboxymethyldextran, biotin, protein G or A, depending on what you want to immobilize in the surface. For example, long-chain dextran coatings are appropriate for small molecule analytes. Small-chain dextran coatings are more appropriate for large analytes. You can also study biotinylated ligands with a sensor coated with streptavidin, or use a lipophilic layer to capture liposomes and lipid bilayers, or use a plain gold surface for custom design approaches. The first step in the interaction analysis is immobilization of one of the interactants on the sensor chip surface. This immobilization can be permanent in the form of a covalent bond or transient by means of capturing. The immobilization technique should be determined based on the ligand type, protein, sugar, DNA, the analyte to be used, small or large interactants, and the purpose of the study, specificity, concentration, affinity, kinetics. In addition, the ligand must retain its biological activity after immobilization. Knowing information about the ligand size, isoelectric point, amino acid composition, pH stability, and possible sites for oriented coupling is important. There are several covalent coupling chemistries available to immobilize the ligand depending on the available reactive groups. 3 well-established procedures are the use of amine, thiol, and aldehyde coupling chemistries. Covalent coupling is stable and, in general, does not require any modifications of the ligand. The mobilization level is easily controlled and the ligand consumption is low. A different approach is to use capturing antibodies or systems to put the ligand in a specific orientation. The affinity capturing system used must have sufficient affinity to the ligand in order to make a stable complex. Some of the systems are completely regenerable, but then the ligand consumption is high and the ligand capturing is not always stable. In addition, the capturing system must not interfere with the function or binding site of the ligand. Now, regarding the experiment design, you obviously know that you should make replicas. You shouldn't believe an interaction curve before you see it at least twice. The flow buffer should be appropriate for the interaction, free of particles, filtered, and the gas to minimize the formation of air bubbles, a great enemy of a SPR experiment. And the flow rate is also important to minimize mass transport effects. Before running an experiment, the baseline should be practically flat. Regarding the analyte concentration, it should be between 0.1 and 10 times the KD if you know it. The injection time should be long enough to give association curve sufficient response and curvature, and the dissociation curve sufficient decay to analyze. The dissociation time should be also enough for at least 5% of the analyte to be dissociated. In order to reuse the sensor chip surface, the analyte must be removed, but the ligand must stay intact. The most frequent regeneration method used is to inject the low pH buffer, but there are other procedures. These are examples of a good and a bad sensogram. As you can see, in the high quality one, the baseline is stable. We can see curvature in association. The ligand is saturating. We have replicated curves and no spikes in the curves. The concentration range is wide, and we can see decay in the dissociation phase. In the low quality one, we can see that there is a drift in the baseline, spikes. The ligand is not saturating, and there's a narrow concentration range. Also, there are no replicate curves, and the decay is low. In the end, after analysis, when you are writing your paper, ideally you should mention all of these items. Now I'll show some application examples in life sciences. In this first example, MP-SPR was used to study the interaction between bovine serum albumin, which is commonly used for drug delivery in blood, and an anti-cancer drug, erlotinib. In this study, BSA was immobilized by amine coupling in a carboxymethyldextran hydrogel gold chip, and then the erlotinib binding to BSA at different temperatures was evaluated by SPR. Here we can see the dose response sensograms at different temperatures, and based on that, the kinetic and thermodynamic parameters of the interaction were calculated. In this other example, the researchers were trying to develop a pH-switchable colloidal system that could be exploited for site-selective anti-cancer drug delivery. They developed a new liposome coating that has a cell penetration enhancer, CPE, and a pH-responsive polymer, which allowed for the controlled intracellular delivery of a model macromolecules and small molecules loaded in the liposome under tumor acidic conditions. SPR studies were performed to further investigate the association of the pH-sensitive polymer with CPE-decorated liposomes immobilized on the sensor. CPE-decorated liposomes were captured and immobilized on SPR gold sensors coated with a carboxymethyldextran hydrogel layer functionalized with dodecil lipid anchors. The pH-sensitive polymer was dissolved in running buffers at pH 7.4 and 6.5 to access polymer liposome association under different pH conditions. At pH 7.4, the SPR response was considerably higher than at pH 6.5. This result confirms that the polymer interacted more efficiently at neutral pH than at acidic pH. In this study, a MP-SPR approach in combination with living cell sensing has been utilized for monitoring drug-cell interactions in real time under constant flow and without labels. The surface Plasmon resonance angle versus intensity plots provide fully specific signal patterns for various cell behaviors when stimulating cells with drugs that use para- and transcellular absorption routes. In this study, the cells grew directly in the SPR gold sensor slide, and then the sensor was inserted into the instrument. The interaction between cells and test compounds were measured by injecting the compound of interest, followed by rinsing with buffer, and the full SPR angular spectrum was acquired every 4 seconds. This study lays the foundation for developing new types of cell-based tools for life science research, which should contribute to an improved mechanistic understanding of the type and contribution of different drug transport routes on drug absorption. In this final paper, they developed a SPR biosensor for selective detection of maize chlorothic mottle virus, MCMV. 11 mercaptolundecanoic acid was applied on a gold surface to form a self-assembled monolayer, and a layer of anti-MCMV antibody was cross-linked on the surface for specific recognition of MCMV. They concluded that the detection limit was approximately 1 parts per billion, which is about 2 orders of magnitude higher than that of the existing ELISA method. And the developed SPR sensor showed highly specific recognition for both purified MCMV and crude extracts from real-world samples. Regarding MP-SPR in material science, the key is the measurement of full SPR curves at different wavelengths. When measured as a function of time, the results can be calculated to many different physical parameters describing the sample properties or interactions. Thickness and the refractive index can be determined by fitting of curves using Fresnel formalism. With additional lasers, a singular solution can be found without knowing refractive index or thickness. The unique wide-angle range measurement enables measurements not only of thin layers from a few angstroms, but also thicker layers up to a few micrometers. The method allows measurements of samples in air, in a specific gas, humidity, or in liquid environment, so no vacuum is required. MP-SPR is a real-time method and therefore allows, for example, measurements of swelling of materials when moving from a dry to a wet environment. It also provides real-time data on material-solvent interactions. This study focused on the efficiency of stabilizers with various molecular compositions and structures to stabilize drug nanocrystals. 5 structurally different polymers were chosen as stabilizers for indomethacin nanocrystals. The affinity of polymers on the drug surface was measured using surface plasmon resonance and contact angle techniques. In this case, indomethacin was deposited directly on the gold sensor, and thickness of the indomethacin layer was also determined by MP-SPR. In this other study, MP-SPR was used to characterize both the thickness and refractive index of a chemical vapor deposition grown graphene films, proving that MP-SPR is a fast and cost-effective method for simultaneous characterization of the thickness and the optical constants of graphene. Here, MP-SPR was used to calculate thickness of the magnetic nanoparticles and polypyrrole layers. These films were constructed for electrochemical detection of methylparaben. In conclusion, we can say that MP-SPR is a method that provides high information content when compared to other methods such as ITC and MST, is multipurpose. As we saw, it has various applications in life sciences and material science, provides real-time detection, is sensitive and accurate, requires small sample quantity, can be medium to high throughput depending on the instrument, and gives you the possibility to perform experiments with unusual systems, for example cells or biological samples without pretreatment. In the downside, functionalized sensors can be expensive, requires immobilization of one of the binding partners, and it may take some trial and error to have the best results. Optimization is key. To finish this webinar, I would like to recommend these resources for further information in MP-SPR. Thank you for your attention, and if you have further questions, you can leave them in the comment section of this video or contact me using this email. For more information about the BioLab, this is our website. Thank you once again. Take care.